I will be explaining you this theorem. Theorem 6.1.4. If V is finite dimensional over F, then T belongs to A of V is regular if and only if T maps V onto V. Okay, this is what the statement. This is if and only if statement. So this proof contains two parts, right? So let us start proving the first part of this theorem. So here you are assuming T is regular. If T is regular, then there will be inverse exist. By the definition of regular, you are writing this. T inverse exist. If T is regular, in the next line, therefore T inverse exist. If T inverse exist means you can write this line, right? T inverse exist means this is what the meaning. T and this is the inverse of T. When you multiply it, you will get 1. Also, or if you are finding T inverse T, then also you will get the answer 1. Then you can say this is what the condition for T inverse exists, right? So that is what you are writing. Now we have to prove T maps V onto V. To prove this, we have to prove Vt equal to V. Okay, that is what you are doing. T maps V onto V means we have to prove Vt equal to V. To prove this, we have to prove, that is to prove this Vt is subset of capital V and V subset of Vt. That is how you will prove, you will do to prove two sets are equal. Right, so that the same thing you are doing here also. So now we have to prove these two. Now first let us prove this. The proof of this is very simple. You are not going to prove anything. You already have a result. Okay, you already have a result. I will show you. Here you can see that result. In that result you have proved Vt is a subspace of V. Okay, you proved it. You can see that. Can you see? Yes, this is that proof. So from this result, you are using this in this proof. You are not proving it, you are just using it. Okay, so here you can write since. That is why you are writing this since. Since Vt is a subspace of V, we have this condition. So first one you have proved. Now our intention is to prove this only. Okay, so let's see how they have proved it. Next, to prove V subset of Vt. So to prove this, you are taking an element from this capital V, that is small v, and now you are taking the small v from this capital V, right? Now what you will say is the small v belongs to Vt. That is how at the end you will bring. Then you can say V subset of Vt. That is what the process going to happen. So here you are taking V from capital V. Like V belongs to capital V. Now you can write this small v like this. The meaning is not changing, right? So you are writing V is equal to V into 1. So in the place of 1, you can put T inverse T from the assumption you are putting. Now you are bringing this to pay as in one bracket and keeping this away from this bracket. You are making a little bit of adjustment. Now this Vt inverse belongs to capital V. Okay, Vt inverse belongs to capital V and this is T. So write it down. This belongs to capital V, right? So that is why you are putting belongs to capital V and put this T. So you will get, so here you look at this. At the beginning you took V belongs to capital V. Now the same V belongs to Vt, this Vt. So you can say from this you can say V subset of Vt. So the two conditions to say V equal to Vt you have proved. So you can write therefore we get V equal to Vt. So you proved the first part. Now we are going to prove the converse part of this theorem. Okay, the converse part is you are assuming T maps V onto V and you will prove T is regular. That is, you are assuming Vt equal to V, right? T maps V onto V means this is what the meaning. You are assuming this and you are going to prove T is regular. So you are going to prove this in a form of contradiction. At the end you will bring the contradiction. So this is that kind of proof. So that you have to take this like this. Suppose T is not regular. If T is not regular means T will be singular. Now what you have to do is you are having a theorem. Okay, you are having a theorem using the singular condition. So you are using that theorem here. since if V is a finite dimensional over F, to use this theorem only you are bringing here singular concept, okay. So here this is the statement: if V is a finite dimensional over F, then T belongs to A of V singular if and only if there exists V1 not equal to 0 belongs to capital V such that V1 T equal to 0. In symbol, what they are trying to say from the sentence is T belongs to A of V if and only if V1 T equal to 0. So here you have to know what is V1. V1 is from the vector space capital V, and this V1 not equal to 0. These are the two conditions hidden in this sentence, hidden in this theorem, okay. So just keep these two things in your mind, and these are the extra things from where V1 belongs to, what is the condition for small v1. These are the things you have to know in extra. These are things you have to keep in your mind, okay. So if you have these two in your mind, then these things will come to your mind automatically, right? So that is why I'm saying. So you are going to use this theorem. So here you have T singular, okay. T is singular, therefore you are getting V1 T equal to 0 in this line, okay. So now in the next line what you are doing is, you are getting this, you will use this, okay. You will use this in the further steps. Let's see how. Now V1 belongs to capital V. Here you have V1 belongs to capital V. You are writing is linearly independent. This V1 is linearly independent. Okay, I have no proper explanation for these lines, okay. V1 belongs to capital V is linearly independent. Then we find these vectors. These are the elements from capital V. The elements from capital V is called vectors, right? So that is why, because this is a vector space, the elements from vector space is called vectors. That is okay. This is an extra information I have told you now. We find these elements from capital V such that this V1, these elements is a basis for capital V, okay. Then every element in Vt is a linear combination. If that's so, then every element in capital Vt, the elements in capital Vt will be the linear combinations of this, okay. That is, elements in Vt will be look like linear combinations of these elements. Or okay, you have to write this paragraph, okay. Keep this in your mind. If you know the more information about this line, then you can understand more easily, right? So here I have no proper explanation on these lines, okay. I have to get to know about it. The time is very less, okay. Okay, I'm preparing for the examination, so that is why I don't have time to research all these things, right? So that is what the problem, okay. Just leave it. Excuses is not acceptable actually, okay. Just keep everything aside. Let's proceed the proof of this theorem. So here you are writing this. Now after that you have v1 t equal to 0, right? You are using that in this line. Here you are getting w1 equal to v1 t. Here you are having value of v1 t equal to 0. Therefore you are writing that w1 equal to v1 t is equal to 0. Therefore v1 t is spanned by n minus 1 elements, because one of the elements is getting 0. Therefore you will get the remaining number of elements will be n minus 1, right? Totally have n elements. From that, one element becomes 0, one term becomes 0, so that you will get n minus 1 elements in that linear combination. That is what you are writing here. Now dimension of Vt in here, this is the dimension of Vt. In Vt you have n minus 1 elements, okay. So just see in the next line what they are doing. Dimension Vt less than or equal to n minus 1, right? Less than or equal to n minus 1. The dimension of Vt is this n minus 1 is less than n. That is obvious, right? N minus 1, here is n. This is, you are subtracting 1 from this n. So obviously n minus 1 will be less than n. And the dimension of V is n. That is why you are writing dimension of V is n. My God. Okay. equal to dimension V. So from this line you can write, combining this you can write dimension Vt less than dimension V. So you are getting dimension Vt and dimension V. The dimension of Vt and V is different. So you could not say this Vt and V are equal, right? So here that is why in the next line you are writing Vt not equal to V, which is a contradiction to our assumption Vt equal to V. Therefore our assumption T is not regular is wrong. Therefore you get T is regular. Hence the proof.